calculuses in group algebras. So I think I can start. I'm sorry for the look of presentation. Google, not Google, Microsoft Teams is a little bit new for me. So what I'm going to talk about, there are different types of the differential equation in spaces which are equipped with some algebraic structure. For example, if you have got a group algebra, as it's all written on my slide, watch, you can look for a linear operator on each which satisfies to the Leibniz condition as in the table, or Fox condition as on the table on the right side. Also, there's a more generalized type of derivations, so-called sigma tau derivations. So if you have got two endomorphisms sigma and tau, then linear map is called a sigma tau derivation if it satisfies to the twisted Leibniz condition. So what I'm going to talk about, there is approach to study these types of linear operators, different types of derivations, with the help of characters on some groupoid. This approach was presented in joint work of me with Professor Mishchenko and Professor Stern about, I think, already 5 years ago. I will give a reference to it. And this method gives several interesting possibilities. First is when you are starting derivations, you can use the structure of the group, so again we have got a space which is equipped with a group action or some group structure, algebraic structure, and it's easy to see that you need some properties of the group to understand how the derivations look like, because in the multiplication which is written in the identities, you see the multiplication you get from your group. So you need to know something about your group to understand how it is working. So this groupoid approach gives a view how group conditions work for the derivations. This is first of all. And secondary, it gives a possibility to join different mathematic constructions together. For example, I will give a view on it. I will formulate the corresponding theorems that, for example, the structure of classical Leibniz derivations in group algebra, it is it is connected with such a strange invariant like ends of group or ends of graphs. And so on. So you have got a connection between derivations and the corresponding homology theory, for example, with Hochschild cohomology and ends of groups. You have got connection between these constructions and coarse geometry, and so on. So this approach gives a new view on this problem and gives some results about which I'm going to talk right now. So I say that we need some characters on a groupoid. So what is groupoid? Groupoid is a category. If you don't like category theory, then you can think about objects of this category just as points, and points are group elements, and you have got morphisms or just geometrically arrows. Arrows are pairs of group elements. If, for example, AG it's an arrow from element A to element B if J of A is equal to B. So lambda is a group action, and you have got the action of element J, which goes from A to B. So you have got an arrow which is labeled, sorry, by element B, and has a source A, and the target B is a result of action of element J on element A. So we can take compositions of these arrows in common way. And two main examples about which I'm going to talk above is two very well known for mathematicians group actions. It's conjugacy and translations. Of course, you can. I'm taking right translations of group, so I'm multiplying by G on the right side. But of course, you can one can take left actions, and that will be another example, but it's similar to this. The results will be similar. So will talk just about right translations. If we have got a groupoid, we can define characters on this groupoid. What is the character? Again, morphisms are arrows. So if you have got two arrows which can be composed, then you can write on each arrow number, integer number, for example, a real number. And on the composition, you must have the sum of the numbers which were written on composing arrows. So this is identity for the character, which talks just about it. For physicians, it means that if you have got two actions, then on the result of them you have got a sum of actions. I will need in this speak mostly so-called local affinity characters, and we will local affinity. It means the condition which is written here, that the value of character on the morphism is equal to 0 almost for all G, and A is fixed. And also we will need a special part of the characters. It's trivial on loops characters, because you have got morphisms which have the source and target which are equivalent, and we will sometimes need the space of characters which are trivial on such on loops, or endomorphisms, if you prefer this term. So main idea, what I'm going to talk about, what is the approach? If you take a linear operator which acts on the group ring, here car is a ring or field that don't care, especially integer numbers or complex numbers. So you can write this linear operator as a linear, in the matrix form, as it is written on linear algebra. And you can take as coefficients the characters. So you have got this form is a form of linear operator, and I think it's rather easy to see, but it's just a calculation on generators, that for such operator holds an identity which is written on the desk. So why I have got this identity? Because if you take alpha on the multiplication GUV, then you can see that you have got a character on the second argument. You have got also UV, And so it means that this is a composition of two characters such that, and this condition for characters gives you some identity. And you can trust me that I calculated it correctly, and this identity will be written in the following way, uh, as it is written in the lemma. So, not a little bit strange identity, but we have got to our examples when we have got a conjugacy action and translations action. And in first case, when the actions of conjugacy, this identity turns to Leibniz rule, and in the second and secondary, if you take as an action translations, you have got another type of identity, and this is an identity which was presented by Forks. The definition that Fox derivatives, he calls it usually derivatives, but I use the term derivation. Fox derivatives are such derivations from group ring to group ring that they satisfy their corresponding identity. And you see, we have got two different groupoids of action. So we have got two different types of characters. And for each of them, we take two different types of differential calculuses, which are well known and which are interesting for other applications and other mathematical areas. Um, Very nice. But of course, you can take other actions, you can take other types of writing this linear operator. You will get other, of course, types of different of quasi-differential equations. We have got another types of identities. But I didn't find other interesting types of such identities. But perhaps some of you can give me an advice. I will be very. That will be very. I will be very thankful for you to you. So first, we solved first problem. We have got um, one description for two different types of derivations, for Fox derivations and Leibniz derivations. Let's look on classical derivations a little bit more precisely. Well, perhaps everybody knows what is inner derivations. It's derivations which acts on element x by commutator formula, as it is written. And the character which corresponds to the inner derivation is trivial on loops. But the opposite isn't true. The set of derivations which corresponding in the view of this formula, of course, which characters are trivial on loops is a little bit bigger than the set of inner derivations, and we call it the set of quasi-inner derivations. A theorem which was proved in the joint paper with Alexander Alexeyev is the following. The space of quasi-inner derivations is an ideal in Lie algebra of all derivations. And it's very interesting to think what is the connection between inner and quasi-inner derivations. Is there a lot of them? So the dimension of quasi-inner by inner derivations, which has support in one component of the groupoid is equal to the to the year of some graph. This I will explain what is this graph a little bit later on the second frame. But what means the letter year? Letter year means the number of ends. It's geometrical invariant. So what is this graph is? This graph is called conjugacy diagram. It is similar to the Cayley graph, and it is defined as following. So you have got as vertices elements of groups, and you have got labeled edges. So the labels are from the generating set of the group G. So you have got an arrow which is labeled by the generating element by generator X if B is conjugated with A with the help of X. These graphs, they are not equal in general to Cayley graphs, but they are monotonically covered by them. And these graphs are not periodic or vertex transitive, but they are, of course, equivalent for different sets of generators. So some pictures. This is a little bit geometrical talk, so it's not very usual for geometric, but I have got pictures. So this is the part of conjugacy diagram for a free group of rank 2. This is the part of this diagram for Baumschlag solitaire group. And now you see that it is not periodic or vertex transitive. It's just a part of the diagram, but it's already a good sign that it's absolutely aperiodic. But sometimes, for example, if you take Heisenberg group or more generally, the nilpotent groups of rank 2, then their conjugacy diagram is equivalent to some Cayley graph. Perhaps there are some other examples of such groups. I don't know, but generally no. Generally, it isn't equivalent to a Cayley graph. So you see, it cannot be a Cayley graph. It cannot be a part of Cayley graph. But sometimes it is. So this is why nilpotent rank 2 groups are good as an example. Well, good example of such groups is Heisenberg group. So again, what about classical derivations? For classical derivations, which satisfy to the Leibniz rule, you can study them with the help of conjugacy diagrams that gives you an information about inner and quasi-inner derivations, and also that gives you information about outer or quasi-outer derivations. So you can find examples of them, you can find the dimensional of quasi-outer derivations, and etc., etc., etc. These results, there are a lot of results. They're not. I don't want to say that I have solved all problems which were in this case, but we can find a lot of such information. Also, like I would like to mention that if you take not the classical group algebra with integer or complex coefficients, but you take coefficients in some finite ring, then also you can work with conjugacy diagrams. You can find outer, quasi-outer, and so on derivations, and this case is rather interesting for applications, but it's another story. So for classical group algebras, for classical Leibniz derivations, we can know about them almost everything. Another case is Fox derivations. You can, let's return to the first slide. So Fox derivations are this one type of derivations when this partial there identity holds. So you can also take equivalent of conjugacy diagram, which is the action diagram, and for Fox derivations, the action diagram is just a Kelly graph of the group. So it's rather easy to prove that all Fox derivations are given by trivial on loops characters, just because of course for infinite groups it's one case, finite groups another case, but anyway, all such derivations are inner. So you can mind about it that Fox derivations are always quasi-inner. And in more usual, I think, case, when the Cayley graph has got two or one end, this is the case. You can find this by the Stolling's theorem. It just means that your group cannot be decomposed as a free product with amalgamed subgroups. Then all Fox derivations are given by formula which is written. You can check that the Fox identity holds for them. And this is a very well-known case of Fox derivations. But if your group looks like free group, then as it was for classical derivations, you can find out some quasi-inner but not inner derivations, and there you can find out the formulas for such derivations, but they are not very nice, so I didn't write them in this presentation. But what we have to understand about this problem, what is quasi-inner not derivations? Not formally. Formally, I have defined them as derivations for which the corresponding character is trivial on loops. But informally, how to understand what is this? It means that your quasi-inner derivation can be written as a formal sum of inner derivations. Formal sum, because this sum is not working in your group algebra. So you have got an infinite number of elements from your group algebra and sum them. This is not this sum doesn't in terms of functional analysis. This is just formal sum. The row isn't fundamental. No, it isn't Cauchy. So this is formal sums and quasi-outer derivations, which are not quasi-inner. It means that the corresponding derivation cannot be written as even a formal sum of inner derivations. It's absolutely non-inner derivations. So another general case about which I have mentioned above, the case of twisted derivations. So you need to work with them, not a groupoid action, not action groupoid, sorry, but you need another twisted groupoid. So each is defined with the help of endomorphisms. Also, you can write the composition and so on. And the theorem, as above, is the following: that sigma tau derivations can be written as local affinity characters on such a twisted groupoid. So you have got twisted derivations, so you have got twisted groupoid, so you have got characters on twisted groupoid to define your twisted derivations. But the formula is similar as it is written here. So then, of course, you have got class of inner derivations, but it's not inner derivations in common sense. It's sigma tau inner derivations, also twisted. And also you have got that there are some quasi-inner derivations that are not inner, but more interesting, I think, example is of non-inner, non-quasi-inner derivations. So this example also works for common derivations, Leibniz derivations, of course. Then you have got just sigma tau identity. So for sigma also again twisted central in twisted for twisted derivations you need twisted groupoid and you need twisted center of it. So we call an element A sigma tau central if each for each v each is twisted commutating as it is written. So by sigma tau central element, you can take an homomorphism phi, and then you can define on basic elements, of course, on basis derivation there by formula as it is written. And this is a sigma tau derivation, and it is not quasi-inner. So you cannot rewrite this derivation as a formal sum of inner derivations. That is a very nice, I think, example, and it's a rather easy example. Of course, you can think, and was people who was working with such types of group algebras that are Johnson, Sakai, and Caddison, Ringrose, and others. They worked with not just with group algebras and algebraic view of them, but they worked with L1 and other spaces over groups. So you need some topology equipment in your group algebra, and we can take norma in group algebra as a vector space. We can take a closure under this norma, and this will be a bimodule over a group ring. And for such a bimodule, we can check whether the norma is subordinated to the supremum norma. So that just means that if an element is subordinated in your norma, then it is bounded in supremum norma. And then the theorem that for such subordinated norms, all derivations are quasi-inner. So I cannot prove that they are inner, and of course that is not true in general. There are some counterexamples. But you can prove that for this very big class of bimodules, all derivations are look like inner. They cannot be very outer. So that's an interesting, I think, theorem, and that gives another new approach to study derivations in L1, in LP, and other spaces. Well, it is a well-known Johnson's problem that whether all derivations in L1 of G are inner. This problem was positively solved by Victor Lazare in 2008. But they are working with L1, just L1 because it is an algebra. And our approach gives a possibility to think about LP. So I'm, well, just from this theorem, which is written here, you get that all derivations in LP are quasi-inner. And my hypothesis is that, in fact, all derivations are inner, so quasi-inner and inner are equal for LP. We, with my student Alexei Nayandin, we have proved this for several types of groups, but the general case isn't easy for us. Finishing my talk, I want to say about two my dreams. Two questions about which I'm thinking and trying to, and I think perhaps they will give you an understanding why I'm interested in this derivations and in this chapter approach. First one is the following. Is it true that derivations in any associative algebra can be identified as characters on some category? So if you take as an associative algebra group algebra, then you must take groupoid of action, then you are welcome. Another my student took results that if you take a semigroup algebra which is generated by Maltsov semigroup, then again you have to take a category, and again everything is okay. Another result I have talked about, that if you take sigma tau derivations, again you take a groupoid, everything is okay. I think that if you take and any associative algebra, perhaps it must be as a vector space be separable, but I'm not sure that it's important. Then you, I think that you can you can find out a category which is equipped, which is connected to the type of basis in your group algebra, and then you will have a category, you will have characters on it, and these characters will identify your derivations. This is a dream. I have some ideas about it, but I'm not sure that it can be solved in this general case. My another dream is much more near to the theme of this conference. It's the following. You have got a group algebra. It is a vector space. You have got derivations there, so you can find out pseudo-differential operators. What is a pseudo-differential operator? You must take some Lorentz series. You can put in Lorentz series as values your derivations, so that will be a pseudo-differential operator. There is an interesting and nice calculation for such operators. It can be found out with the help of ideas of Maslov and with ideas of Parshin. So I think that if you have got an algebra of pseudo-differential operators, if you have got the calculus for such operators, which looks like absolutely as calculation for classical pseudo-differential operators, then you can find something which looks like Sobolev spaces, and then you will have some kind of Atiyah-Zinger theorem. That is interesting question to think about for me. I'm thinking about it. It's interesting for me, so you can try to think about it also. So that's it. I tried to talk you about these results. So as you see, there are a lot of different types of derivations, and a lot of them can be connected together through the categorical theories, through chapters on the corresponding groupoids. So that's it. My speak is finished because I'm a chairman. So I will ask you whether you have questions, comments, suggestions. Well, as I see, everybody is sleeping, so no comments. Thank you. This part of the this section is finished. We have got, as I remember, the break now, so it